Okay, so our next and final speaker of the morning is William Hornslien, who's going to tell us about polyhedral products in motivic homotopy theory.
Yeah, I first would like to thank the organizers for giving me the 6-hour talk time slot. So, because we have a lot to cover for sure, because this is not a motivic conference. But, so I just hope you're ready, right?
We are motivated.
But we'll see where we'll manage to get in 45 minutes. So, like the quick explanation, right? Because you all know what polyhedral products are, so that's fine. The motivic homotopy category, you just start with the category of smooth varieties, and then you make it into a growth index site with like the Nesnevich topology, and then you have to take smooth presheaves, and then simplicial presheaves, sorry, and then do some localizations to get the motivic homotopy category. But luckily, the talk is not going to be like that, so we'll start out with some familiar pictures. So, roughly 20 years ago, there was I think the first toric topology conference, and in Japan, if I've understood correctly, and to that conference, Buchstaber and Ray wrote an invitation to toric topology. And in this, I guess, invitation, they define what they call the toric tetrahedron. And in one corner, we have topology, and we have toric algebraic geometry. And up here we have combinatorics. And in this back corner we have symplectic stuff, which I don't know anything about, so we'll stay away from that edge. So toric topology where we're now is all around, moving around inside here, or at least close, I guess, to this edge right here. And the edge we have here can in many ways be thought of as looking at the complex points of toric varieties. That's what's going on here. But there is also another way to combine topology and algebraic geometry, and that's through motivic homotopy theory. But before we reach the motivic homotopy theory, we're just going to actually review some polyhedral products, because that's nice and easy. Okay, we can do it up here. As we saw in Taras's talk, is that you can really do polyhedral products in almost any category as long as it's nice enough. And in Taras's talk, he confined himself to looking at just normal colimits and working in categories where you have colimits. But there are other categories where you have access to homotopy colimits. And we can make sense of polyhedral products in those categories. So we'll just say that C is some suitable category. It can be a model, infinity, as long as it has enough homotopical properties for us to work with. So what we want homotopy. I will do homotopy colimits, right? And we need products. That's really it. So so how do we do this? We just pick objects in our category, pairs, AI, BI, and some maps between them, where AI are objects in here, FI is some morphism between them, and then we do our usual thing, right? We define our polyhedral product to be the homotopy colimit over, I'll call them these sigmas, and the sigmas live in K. and the sigma is just a big product of yi's where yi is xi if I is in sigma and ai if I is not in sigma. Classic stuff. And throughout this whole talk, I will probably not see, there will not be a single normal colimit, which means, or all colimits will be homotopy colimits, which means there might be cases where I'm skipping the two first letters of colimit, or of homotopy colimit, and just writing colim or saying colimit when what's going on in the background is a homotopy colimit. Okay, so we've now set up our polyhedral products, and we're just working in some kind of category. And now I want to impose a couple of more conditions on our category. I want products to commute with colimits. This is something topological spaces has, or the category of nice topological spaces already has, and it's a fair thing to assume. And one of the nicest theorems, I think, in classical toric topology is the BBCG splitting. A little bit larger, there we go, which essentially tells you what happens to your polyhedral product when you suspend, and it splits into nice wedge of spaces. And in some special, or a special version of it, I guess, is when your spaces, when you just look at the cone on some spaces A, then this is homotopy equivalent to a big wedge where we run over I, not in K, double suspension, geometric realization of the full subcomplex here, smashed with the correct A's here. Or, yeah, let's write it like this. Nice and all this is in topological spaces. And I guess the first result is, I guess we'll call it a theorem, and then also gotta appreciate the the ones that proved it first, is if we start with a category C, now it can be model, it can be infinity, whatever, and we need this property that the products commute with colimits, which can also be that C is Cartesian closed. It's another way of doing this. And we, of course, need colimits to exist in our category, so we need small or finite colimits, or finite homotopy colimits. Then this thing still holds. So I pick objects in my category, I take cone objects, and I do my polyhedral product in whatever category I am in. And things look like usual. The only question is like, what is this guy? What does this mean in a different category? So what's your question? I'll repeat it. Yeah, so smash product is just going to be defined as this push out, right here, where x and y are pointed objects, and then you created the wedge of them. Yes? Yeah, I think it is. I suspect it is, as long as we're working in nice enough places. Is it okay?
Yeah, I'm just wondering why it happens in your favorite category. I mean, do you need any extra property with your category?
As far as I know, you don't, but don't quote me on that. At least it's true in the categories I care about. So,
Questions like, what is the suspension or what is the circle in your category?
so yeah, that's a. So let's start. A circle in my category S0 will. Well, my category will have some terminal object as long as I guess I gotta assume my category has a terminal object. But then S0, or what we will call S0, is just going to be the homotopy colimit of this diagram right here. Just two where these guys are terminal objects. That's going to be S0. And then you can start, if you do suspensions of these, of the thing that comes out here, you'll get the guy that looks like S1 in a way.
So what about graphs? Category of graphs and category of digraphs, are they in your belong to your category?
I don't know. It's, because I've cared more about homotopical categories with homotopy-like properties. So things that look like topological spaces, but maybe with a twist. So let's get some example categories right away. Examples. So of course it's going to be topological spaces, or the category of nice topological spaces, CW complexes, for example. Or you could do G equivariant spaces. Oh, now I got to write larger again. Spaces. You can also do more algebraic-like categories, which derived categories of chain complexes. And of course, the main actor of the talk, the motivic homotopy category. So those are some examples. So we'll now move on to the motivic homotopy theory section. And the main thing to take away from this first part was that the BBCG splitting holds in many other places, in particular in the motivic homotopy category. Oh, yeah, I have to explain what K sub I is. So here I explain what S0 looked like. Imagine that you keep on doing this and you can build a thing that looks like your simplicial complex in a way. Or you can explain it as you take the face category of K restricted to I, and then you remove the initial object in this category, which is corresponding to the empty simplex. And then you take the homotopy colimit of that diagram, where all the objects in the diagrams are just the terminal objects. That is this guy living here. So in topological spaces, that's just the same as the geometric realization. But if I, for example, were in the category of chain complexes, where chain complexes of abelian groups, and I do this, then I get a chain complex that has the homology of Ki. Does that make sense? Good, great, thank you. Okay, so we'll now move on to motivic and do a very soft introduction. So the first question is, what is this? What is motivic homotopy theory? Well, it's a homotopy theory for smooth algebraic varieties. So these are the guys that show up in algebraic geometry, and in algebraic geometry world, these guys are kind of like manifolds. In fact, if you have a smooth algebraic variety and you look at over C and you look at the complex points, it's literally a manifold. Or algebraic variety can be changed with the word scheme. It's fine. And the simplest pieces of the smooth algebraic varieties are the affine varieties. So an affine variety is just like the spectrum, the Zariski spectrum of some ring R. These are like the simplest pieces. And general algebraic varieties are built by gluing these guys together. So this is what motivic homotopy theory is. But why? Why do we care? Well, throughout history, people have found a lot of invariants in algebraic geometry that are A1 invariant. What that means is we have this variety that is very important to us, which is called A1, which is defined to just be the spectrum of the polynomial ring in one variable. And this is the affine line. And if alpha is some kind of algebraic invariant, there are several examples of algebraic invariants where y is some guy in my smooth algebraic varieties. I'll call the category of smooth algebraic varieties of finite type or whatever SMK over a field K. So we'll just pick a base field and we work over that. But alpha is some invariant. Then in many cases, we have that alpha y is the same as alpha y cross A1. Just like if I take several, or essentially all of the invariants we work with in homotopy theory or in topology, algebraic topology, don't change value when I time something with the interval, because the interval is contractible. So the goal of this homotopy theory is somehow we want a homotopy theory for algebraic varieties where A1 plays the role of the interval. And how do we do that? Well, that's the annoying thing. Some work has to be done. So we start with this category of smooth algebraic varieties, but that for some reason doesn't have all the colimits that we need. So one way of getting colimits is to create simplicial presheaves on this category. It's not that important for us right now. And then now we're in here, we have all our colimits, but A1 is still not contractible. So you can localize with respect to A1 and say A1 is weakly contractible, like you can localize classes of morphisms in a model category. And with that, you can create the category of motivic spaces, SBCK, and its homotopy category is what we'll call curly HK. And that is where we'll be working. But this construction isn't that important for what we're going to do. First, we want to just see what are some example objects that can show up in HK. So all algebraic varieties, smooth algebraic varieties can show up. So our guy Hornslien from before, he's in here. And one good way of making sense of what's going on in the motivic homotopy category is looking at the real points of whatever you're dealing with and the complex points of whatever you're dealing with. So it's a good slogan at least. So here what is the affine line over R? What is well, it's just the number line. It's just a line. And the line is contractible. Good. what's the affine line over C? Well, that's going to be the complex plane. Great. Not too difficult. Then we'll step it up a notch. Another central guy, which we'll see more of later, is GM. And GM is just defined to be the punctured affine line. So it's the affine line, but without the origin. So over R, this now looks like an S0. It's two disjoint pieces that I can contract. And over C, it looks like the punctured plane. So I'll draw like this. And the punctured plane is homotopic to an S1. And here we have homotopic to an S0. And we have more examples, of course. We have, for example, A2 without the origin. So I have to take the product of A1 with itself and then remove the origin of that. Well, over R, it's just going to be the same picture as I drew over here. It's going to be the punctured plane, and it's going to look like an S1. But over C, it's going to look like C2 without the origin, which looks like an S3. And we can check out some more examples as well. You have projective algebraic varieties as well. And our slogan for now is still going to be look at the real and the complex points to imagine what they look like. And the projective line is just a compactification of the affine line. So the real picture here is just going to be a circle, where this is my point at infinity. And the complex picture is going to be a sphere. Good? But there's one more type of object in this category that will be central, which comes from this weird process that we did when we created simplicial presheaves or whatever. And that's topological objects also exist in this category. And they're somehow represented by, you just take a simplicial presheaf, which is a presheaf that has values in simplicial sets, and you take the presheaf that constantly maps to some simplicial set. And a simplicial set is just a topological space. So for example, I'll have the space I'll just call S1, for example. And this is the simplicial presheaf that just always maps to a simplicial set that is S1. So over R, we'll just say that this looks like a circle, and it still looks like a circle. And so for example, in the motivic homotopy category, this weird realization thing of this simplicial complex guy is just going to be a constant simplicial presheaf mapping to the geometric realization of this guy. So that's a lot of words. But on this board right now, there's a lot of sphere-like objects going on. And so we'll briefly talk about spheres in the motivic homotopy category. So the motivic homotopy category has bigraded spheres. What does that mean? Well, it for some reason means that we have two spheres that essentially generate all the other spheres. One is this, the topological sphere, the simplicial sphere, the one coming from topology. But we also have one that is more geometrical in origin, right? We had the affine line, which is the interval. How do you define S0? Well, you take the boundary of the interval, and that's what we did here. We removed the origin. So GM is our other interesting sphere. And we'll label them as follows. I'll just define S10 to be this guy, S1 from here. And I'll define S11 to be our guy, GM. And we'll now look at one more example of how to create yet another sphere, just to give a flavor of how this homotopy theory works. Is in algebraic geometry, when you create the projective line, you can find a cover of the projective line where you cover it by two affine lines. So you take, if we look at this picture, it's like taking a line going across the top here, and then let's get it another color, and then taking another line that runs like this. And their intersection is then just going to be a GM, which is this guy. So we have a picture that looks like this. And there is a theorem that says if you have a Zariski cover, like a nice cover of your algebraic variety, that's a homotopy push-out or a homotopy limit, co-limit in the motivic homotopy category. So this is a push-out. But the good thing about homotopy co-limits, right, is that they're homotopy invariant. So an A1 is contractible in the motivic homotopy category, which means it's the same as a point. And I've not said what the point is, but the point is just a spectrum of whatever base field I chose. So this picture I have here gives me this other push-out square that gives me the suspension of GM. And it shows that P1 is the suspension of GM. So now if we play around with the gradings, we'll see that P1 is S10 smash S11, which is S21. Okay. Now we've done our spherical duty and the setup. It's time to get to the moment angle complexes. So goodbye ferry terminal. So motivic max. So in the beginning, we saw that we can just do polyhedral products wherever we want, or in nice categories. And here we have a nice and new category that looks like topological spaces in a way, but not completely. And we'll just define the motivic moment angle complex to be this polyhedral product right here. So examples, if I just do of a point or a single vertex, that's just going to be an A1, which is contractible, kind of expected of a moment angle complex. So what happens if I put in two disjoint vertices? Well, this is going to be, or let's say homotopic too. Homotopy colimit of a diagram like this, GM cross GM, mapping into A1 cross GM, GM cross A1, and we want to compute what this is. And if you know your homotopy theory, you might just immediately see that, oh, this is a join. And then you can do join tricks, and you see, okay, this is an S3 too. Fine. But we can also look at this in a different way. Like I said, with this trick is that Zariski covers are homotopy colimits. And what I've written here is actually a Zariski cover of an algebraic variety. And even one we've seen earlier. So we can just draw a picture. GM cross GM kind of looks like, over the reals, looks like four squares like this. And we just wanted to take the union with A1 cross GM, which looks like this. And then we want to do another union. I'm sorry that I'm doing my unions downwards, but with this, taking these unions, I get this picture here, which is the punctured affine plane. Punctured affine plane. So this is the same as A2 without the origin. And in general, it turns out that there's a different way of looking at moment angle complexes as complements of coordinate hyperplane unions. Or intersection, okay, what? But that still holds here. So we can show that CK A1 is the same as AM without the zero set of something, and that zero set actually turns out to be the ideal generated by the Alexander dual of the Stanley-Reisner. Alexander dual of the Stanley-Reisner ideal of, well, you can put Alexander dual wherever you want in this case, but Stanley-Reisner ideal of the Alexander dual of the simplicial complex K.
Could you say what S32 is in terms of S10 and S11?
Yeah, I'll repeat how we construct this guy. Well, this is going to be S10 smash S11 smash S11. So it's two copies of GM smashed with one copy of the simplicial sphere. Okay, so, and we can do one more example, is that Z, if I do the boundary of an M simplex, then this guy is going to be homotopic to A2M plus 1 without the origin, which is an S2M plus 1 M sphere. So just like in classical toric topology, that when we look at the moment angle complex of boundaries of simplices, we still get spheres. So that's a good sanity check. So now there's a lot of spheres going around, and we have these real and complex pictures of things. So you might wonder, what's the connection? But you can ask your question first. Well, two disjoint vertices is the boundary of a one simplex.
So it's an 3-1 or 2 or maybe 2.
Oh, yeah, there's a plus 1 here, I think. Okay, thank you.
Could you just say what a disk is?
So a disk so the trick I used here is the disk is kind of this guy, or a product of two copies of this. It depends on which field you're working over, which pictures you're looking at, right? Do you want to think of A1 as a line, or do you want to think of it as a plane? Is it a disk? Is it not a disk? So it's kind of weird thing. But the disk is what you want it to be. It's probably a good way to say it. Okay, so what's the connection between our motivic moment angle complexes and the normal moment angle complex, or the classical ones? Well, we have something called realization. Which essentially is, like, we're working over different, or we can pick base fields in our motivic homotopy category, but if the field I'm working over is a subfield or is contained in the complex numbers, then I have something called complex realization, which is essentially you just look at the complex points of whatever guy you have. So this is you could say a functor from HK mapping into topological spaces. And similarly, if K is a subfield of the reals, you have something called realization, which also leads to top, or it's E2 equivariant top, but it's not that important. And in this case, like if I do the realization of my motivic moment angle complex, I get this polyhedral product here, which you can show is homotopic to, or deformation retracts onto the normal one. Yes, what's your question?
Each case must be category.
Yes.
But the function is into the category of.
Okay, yeah, I guess we can change this to go like this then, or put homotopy category of topological spaces there.
I have a suggestion. If you have a question to ask, put up your hand, and then Ian can take the microphone to you, and the people online will be able to hear the question. It's just a suggestion.
Tony's, oh, no, the people online don't need to hear Tony's suggestion.
But, so we have, yeah, this is the complex realization. It gives you the normal classical moment angle complex. If we do the real realization, you guessed it, we get R star, K, this polyhedral product here, which is the same as the real moment angle complex. So there's some connection here to the normal, or to the classical moment angle complexes. And now let's look at the BBCG split, which is just going to be, you can just write it out, the suspension of this guy is going to be homotopic to not in K, and then we want to do two suspensions here, and then smashed with a lot of copies of GM. And then you can show that this is just counting your spheres, the degrees of your spheres correctly. I not in K, Ki smashed with S, 2 plus I. My I, okay, or the size of this set. So with this, now we can actually do some cool things that we weren't able to do before, but there's a question in the back. But Ian is running, that's good.
So presumably that suspension is smashing with S10.
Yes, it is.
Is there a splitting if you smash with S11?
I don't know. That's because it's the weird thing with S11 in motivic homotopy theory is that when you try to do homotopy theory, it behaves very much like an S0. And if I smash with an S0,
So nothing would happen.
yeah, it's just going to be whatever I had from before, but not really, right? Because it's something weird. Okay, Ian is running.
Thank you. When the motivic people are talking about the homotopy groups, the stable homotopy, when they convert their spectral sequence into information about the homotopy groups of spheres, so their spectral sequence is bigraded with both spheres.
Yes.
So how do both spheres convert into one suspension when they forget?
Oh, it's like we can look at our pictures again, right? So when I look at the complex points of a GM, it looks like an S1. And when I look at the complex points of my constant guy, that's still going to be an S1. So if I smash them together, and we're working in nice homotopy land, right? Then it's just going to look like an S2. So that's how it works. What's your question, Ian? Three?
S3.
S?
S3.
Oh, no,
Oh, S2, sorry.
yeah, I just smashed two ones. That's going to be 2, last time I checked at least. So this thing can give us some good stuff. I don't have too much time, so I'm just going to list some things it can give us. For example, it can give you motivic cohomology cohomology as modules over the cohomology of the point. Because for some, motivic cohomology is a very difficult thing to do. It's bigraded, and we don't know the cohomology of the point, which is a problem, but it's still something, right? And using this decomposition of the motivic cohomology groups as modules, let's go here to do the final things. Just to show, like now I've brought all this to motivic land, and can it give anything back to toric topology is the question. And this motivic cohomology thing can, in one way, do. So I'm going to skip a couple of lines of computation, but you can show that I'll just write it like this. The motivic cohomology with some coefficients is going to be the same as this sum I not in k. I want I there's some annoying things to be done, but and we'll just say that A is the motivic cohomology of the point with some coefficients. And then you can show that at least if your simplicial complex has the property that all the full subcomplexes split into wedges of spheres after suspension, then you can show that this guy is some funny sum of these cohomologies of the point shifted around, and with respect to some Betty numbers of, or these are just classical Betty numbers. So there's some kind of like you're spreading your cohomology out across whatever, but it has like source. You can think of, if I draw a picture, I don't know what the cohomology of the point is, so it lives here and it might look like something big like this. But a sphere is then going to have, well, it's going to have a copy of the cohomology of the point in degree 0, and it's going to have, say, it's a sphere that the top class lives here in degree ij or something, then it's going to have another copy of the cohomology of the point up here. That's the point. So we can do this, and with this description here of the motivic cohomology in terms of modules or cohomology of the point, we can define bigraded Betty numbers for these guys, which is, right, I just call beta ij motivic of my guy, CKA1 is going to be, it's 1 if I'm in degree 0 or in here, and then it's going to be some sum of I not in k, I equals j, b I minus j minus 1 ki. ij not equal to 0, 0. Okay. So now I define some bigraded Betty numbers, and as you probably know, is that we can define bigraded Betty numbers on the classical moment angle complex as well, because it's a Tor algebra and it has 2 degrees, and there is a connection. There's a bijection. So I have, I can write Bij motivic of Zk A1. It's just going to be the same as b minus I to j of the classical guy. And so that's, you can compute the cohomology of zk without making it bigraded at all. But now you can argue that the reason that zk is bigraded, or the cohomology of zk can be made bigraded, is because it's an image of what's going on up in the motivic world, which is, maybe sounds a little bit crazy, but that's what it is. That the fact that we have bigradings upstairs somehow forces there to be some extra structure downstairs. So I think that's where I'll end, or I'll say one more short thing is, so now I just showed how this can somehow illuminate what's going on classically, but this splitting also has helped me to compute something called A1 or cellular or A1 homology of these guys. And cellular A1 homology, it sounds silly, is a relatively new thing with very few computations. And using this machinery, not only in the category of motivic spaces, you actually have to use it in some derived category to do some stuff, gives you new computations in motivic homotopy theory that weren't possible before. And it also gives, like, if I pick my simplicial complex to be the triangulation of an RP2, it, for example, gives me an example of a space that has torsion or integral torsion in its cellular A1 homology, which is something that didn't exist before. Thank you.